Okay, so let's see the exercises now. So let's first see what the first one asks. If U is an ideal of R and 1 belongs to U, then prove that U is equal to R. Note the way the exercise has been given. We are not saying anything about R. It's understood that R is a ring, and also since we are mentioning the unit element 1, it is also understood that R has a unit element which now belongs to the ideal U. We then have to prove that U is equal to R. So this one is rather easy. The first few exercises will be easy. The difficult ones will come after some time. We already know that U is a subset of R. Okay, I feel I should mention something at this point about this notation, which I can't remember exactly if I mentioned this before or not. By this notation, we mean that U is a subset of R, or Herstein means that U is a subset of R. The same thing if Terence writes, he would write like this. For tau, this is the subset relation, the notation for the subset relation. However, Herstein means the same thing using just this one. Okay. So now we have to show the reverse inclusion is also true. So let R be any element in R. We need to show that this small r is also in U. Since 1 is in U and U is an ideal, we have R equal to R1. This will also be in U because U follows the multiplication by ring elements from the left. So that's why we can, since 1 belongs to U, so R1 will belong to U, but we know that R1 is nothing but R. Hence, R is also a subset of U. Combining these two containments, we have U equal to R. And this completes the solution. The first one is quite easy. Now we look at the second one. If F is a field, prove that the only ideals of F are the zero ideal and F itself. That is every field, because fields are also rings, special types of rings, where the non-zero elements form an abelian group under multiplication. That's the definition of a field. So, like rings, they will also have ideals. Now, the zero ideal and the ring itself are always ideals in any ring. Apart from that, we have to show that fields have no other ideal. Okay. So let U be an ideal of F that is different from the zero ideal. So our aim now is to prove that U is nothing but equal to F. So since U is not the zero ideal, there will be a non-zero element in U. Choose a non-zero element U in capital U. Okay. Since F is a field, we have U inverse in F. Because U is a non-zero element, and U, after all, being in U means being in F, capital F. So small u is a non-zero element in a field, so it has an inverse according to field property. Since U is an ideal, we have 1 equal to U inverse U. This belongs to U. Why? Because small u is in U, and since capital U is an ideal, so we can multiply this element from the left by this ring element or field element U inverse, thus giving us the fact that the unit element belongs to U. Now we can use the previous exercise. So by the previous exercise, U is equal to F. Hence, the only ideals of F are 0 and F, and that completes the solution. Then the third one. Prove that any homomorphism of a field is either an isomorphism or takes every field element. Am I phrasing it correctly? Or takes each element. Okay, same thing, I can change the language a little bit, keeping the meaning same. Every field element onto 0. So this one asks us to show that if we have a ring homomorphism whose domain is a field, range is of course some ring. If the domain is a field, then either it's an isomorphism, either it's a one-to-one map, or it maps every field element onto the 0 element of that range ring. So let us start by considering such a homomorphism. Let R be a ring F be a field and phi from F into R be a homomorphism. Okay. Now we know that the kernel of phi, we have a notation for this I of phi. The kernel of phi, because it's a ring homomorphism, is an ideal of the domain ring, which is nothing but a field now. Is an ideal of F. So I of phi is now an ideal of a field, and just now in the previous exercise we have proved that the only ideals of a field are the zero ideal and the field itself. So by the previous exercise, either I phi is the zero ideal or I of phi is F. Now we know from the first lemma of the previous section means section 3.4, that okay, not the first lemma, it is something else before that a ring homomorphism is an isomorphism if and only if its ideal is the zero ideal. Its kernel is the zero ideal. So in this case, if this is the case, then our homomorphism is an isomorphism. However, if the other thing is true, what does this mean? It means that the kernel is the whole domain F. So that means every element of F is getting mapped onto the zero element of R, and this is what we had to show. So we can write like this. In the former case, phi is an isomorphism. And in the latter, phi maps every element of F onto the zero element of R, and that's what we had to show. Okay. You can see that we have been going on using one exercise to solve the next. A good set of exercises goes like this. Not all of them follow from the previous ones, but some of them, they come in clusters. Okay, now next we look at another exercise. Now this one provides us with a way of generating ideals in any ring, in any commutative ring. If R is a commutative ring and we are considering an element A in R, then there are two parts. Show that AR by ARB mean the set of all elements which look like this AR, where R is any ring element, is an ideal of R. B. Show by an example. Okay, is an ideal of R means a two-sided ideal. Actually, two-sided is mentioned in the exercise, but since we have said before that we are not going to, for us ideal will mean two-sided ideal, unless of course we are explicitly mentioning something else. So we don't bother to write two-sided. Okay, for us ideal means two-sided ideal. But if the ring is not commutative, then things can go wrong. Show by an example that this may be false. If R is not commutative. Right. Now, first part is quite easy. It's a routine verification. The second, however, you have to think of it for some time, but one can come up with such an example. One just has to look at the examples of non-commutative rings that we have seen previously when we saw examples of rings. And of course, when we say non-commutative ring, the things that come to our mind are matrix rings. So we will use one such example. So let's first of all solve the first part. Okay, so we have to show that AR is an ideal. Note that AR is non-empty. It's not the empty set. One thing I should mention at this point is that this happens sometimes, that while showing that a subset, say we have a subset H of a group, just saying, because to prove that AR is an ideal, we first of all have to show that AR is an additive subgroup of R, then only the second condition will be verified. So in showing that a subset is a subgroup of a group, if you go like this, see, the usual procedure is just this. You go like this. If A and B are two elements in H, and you can show that AB inverse is also an element of H, then H is a subgroup of G. But this is only partially true. You should recall that subgroups first of all have to be non-empty subsets. Okay, empty set cannot be a subgroup. So now this condition is true, unfortunately, for the empty set also. You can probably understand how this is true. This implication is vacuously true. So if we just assume this to be the condition for checking whether a subset is a subgroup, then that is false actually. We have to first of all make sure that H is non-empty. Then only we can apply, I mean, we can apply this one, but without non-emptiness, we have this empty set also included. And that clearly is not a subgroup. So that's why, first of all, we have written that AR is non-empty, which is the case because you see, AR is what? AR is the set of all multiples of A from the right by ring elements. From the right we are saying because it is written like that. However, it's given that R is commutative, so it does not really matter. But the point here is that since R itself is non-empty, this is non-empty because there are multiples. Okay, so AR is non-empty. Now let R1 and R2 be two ring elements. Then AR1 minus AR2 is equal to, according to calculations in ring, A times R1 minus R2. Here basically we have used the left distributive law but along with some other things. Now look at this. Since R1 and R2 are ring elements, R1 minus R2 is again in R. So this is again such a multiple of A. So this belongs to AR. Hence, this is a subgroup of R under addition. Also, for any ring element R, we have AR1, since this is one element in AR we have already considered, so we are keeping that like that. And we are taking a ring element R. This is equal to, or I should have written the other way, RAR1. This is equal to AR1R. And why am I able to write it like this? It's because R is given to be commutative. Now using associative law of multiplication, I can write it like this, R1R. So this again becomes a multiple of A by the ring element R1R, because R1 and R are two ring elements, so their product is also a ring element. So this again belongs to AR. Hence, AR is an ideal of R. Okay, now we come to the relatively more difficult part, B. It's not that difficult, you just have to know the right thing. Let R be the ring of all 2 by 2 matrices with rational entries. The entries inside those 2 by 2 matrices have to be rational numbers. So that type of matrices we are considering. And we have to look at this. A subset is not an ideal. You see, we are supposed to consider subsets of the form AR. since an element now is a 2 by 2 matrix, so we have decided to choose this one, this matrix, where the entries are of course rational numbers. So now we are claiming that this is not an ideal of R, but why? This is because what is the reason? 1 0 0 0, this matrix itself belongs to this subset. And why does it belong to this subset? Because you see, you have to consider multiples of this matrix. On the right side, you can consider the 2 by 2 identity matrix. Then the product will become this itself. So that's how we get this matrix inside this subset. That is okay, but this product does not belong to the subset. 0 1 1 1 and 1 0 0 0, which is equal to what? 0 plus 0 0, 0 plus 0 0, 1 plus 0 1, 0 plus 0 0. This does not belong to this. Okay, by the way, what is the reason for it to not be in this subset? Let us look at a general element in this subset. A general element looks like this. Times some other matrix where this A, B, C and D are rational numbers. Now if we carry out the multiplication, what do we get? A plus 0, A, B plus 0, B, 0 plus 0, 0, 0 plus 0, 0. So you can see that this can never be equal to this. Irrespective of A, B, C and D, choices for these 4 rational numbers, this cannot be equal to this. Why? Because this second row, first column elements are different. They are fixed and they are different. So they can never be, these two matrices can never be equal. That's why this matrix does not belong to this. Now what have we shown here? We have chosen an element in this subset, and this is an arbitrary ring element, and we have multiplied these two, but the product does not belong to the subset. So it violates the second condition for an ideal. So it cannot be a two-sided ideal or an ideal. And there the solution ends. Then just like this, we have yet more ways of creating ideals in rings. Exercise 5. If U and V are ideals of R, then we are defining a set. Let U plus V be the set of all elements which look like this. That is the sum of all elements of U and all elements of V. such sums have been collected, and that collection is called U plus V. Prove that is an ideal of R. Okay. First of all, since U and V are non-empty, U plus V is also non-empty. Although we have mentioned it here, we are not going to do the same thing again and again. Okay, every time we are not going to write that. When we are showing that something is an ideal and we haven't mentioned anything explicitly about the set being non-empty, it should be assumed that we are assuming it implicitly. And that is the case, that is true. If something is wrong, then of course we will write it. We will mention it explicitly. So anyway, so we get down to the actual verification. So let U1, U2 be two elements in U, V1, V2 be two elements in V, and R be any element in the ring. Okay. Then U1 plus V1 is an element in U plus V, like that. U2 plus V2 is an element in U plus V. So these are actually two arbitrary elements in U plus V. Since the elements look like this, so we anyhow had to choose U1 and U2, V1 and V2. And this, using basic calculations in a ring, we can write it like this: U1 minus U2 plus V1 minus V2. Now since U and V are ideals in R, so U1 minus U2 will be in U and V1 minus V2 will be in V, because these two are additive subgroups. Being ideals, they are additive subgroups of R. So this belongs to U plus V. Now, you may feel that some of these exercises are so easy and you are so familiar with these things that they are almost trivial. Yes, they may be trivial to you, but no matter how trivial something is, there are many things beyond these symbols or behind these symbols that have to be taken care of carefully. Okay, if we start taking everything in a trivial sense, to the point that we start making mistakes, that's the point we should stop ourselves and consider the fact that these things are not that trivial. Okay, once you let your guard down, the mistakes start to happen. Okay, so what have we shown now? We have shown that U plus V is an additive subgroup of R. So U plus V is a subgroup of R under addition. Also, okay, now we have to verify the other ideal property, the other condition for an ideal. Also, R times U1 plus V1 equal to RU1 plus RV1 this belongs to u plus v, and u1 plus v1 times r is equal to u1 r plus v1 r. This also belongs to u plus v. Since now in these two calculations we have of course used the distributive laws. Now the reason for these two to belong to u plus v are this: since RU1 and U1R are elements in U, and RV1 and V1R are elements in V, and that is because U and V are ideals. Hence, and that completes the solution. Note that we need not actually carry out this calculation involving addition. Do you see why? We already know that u plus v is an additive subgroup of R. Why? You see, as far as group properties are concerned, our binary operation is addition, and this is an abelian group. What is u plus v? We already know about u plus v, although it looks like we have defined it here for the first time, but that's not the case. We already know what u plus v is. U plus v is nothing but the product of the two subgroups u and v in this group. You see, if you recall, if you have a group G and you have two subgroups H and K,